Okay, hi everyone. My name is Guy, and I'm going to tell you about some joint work with Dean Duron on new near linear time decodable codes closer to the GV bound. In this work, we're interested in linear error correcting codes. So our codes, because they're linear, they're subspaces, and we're just going to consider binary codes. So each code word will be n bits, and the subspace will have some dimension k less than n. We want our codes to have high distance, meaning if you take any two code words, elements of our code, the number of bits differing between them is at least d, is for some large number d. And the reason this is desirable is because it means that if we have some code word, and an adversary corrupts some small number of bits from it, we can uniquely figure out where we came from and undo the adversary's corruptions. The rate of our code will be k over n. And what this tells us is how much redundancy is there in our code. So we start with a k-bit plain text message, and then we can encode it as an n-bit encoded message. And so we want n to be not so much larger than k, which is a measure of the efficiency of our code. And in particular, we're interested in the trade-off between rate and distance. So just normalizing everything by n, fixing the distance, d over n, what is the largest rate, k over n, achievable? Okay, and in particular, we're interested in a high distance regime, which for binary codes, the best we can expect is about a half. So we're interested in delta roughly a half, a little bit less. And in order to characterize the rate of a linear code, it turns out it's really easy. The distance of a linear code is just the minimum weight of a non-zero code word. So what this means is we want linear codes where every non-zero code word has close to 1/2 of the elements be 1, 1/2 minus epsilon. Okay, and we're actually going to have a second requirement that in addition to having lots of ones, we also want to have lots of zeros. So we're going to ask for every element of our code to have close to half ones and half zeros. And this is enough to guarantee that we have a distance close to 1/2, depending on this parameter epsilon. And it's a little bit stronger because we also have this upper bound on the number of ones. But it turns out that essentially every code we know how to construct that has high distance is also balanced. It's kind of got both the symmetrical behavior for zeros and ones. So this isn't really much of a restriction. And we introduce it because in a few slides, you'll see another object that's equivalent. And it's nice to be able to reason about both of these objects at the same time. Okay, so what's the best trade-off between rate and distance that we should expect? Well, a random linear code with rate epsilon squared is epsilon balanced with high probability. And remember, the distance is roughly a half minus epsilon. So because we're working in the high distance regime, I'm always going to talk about epsilon rather than delta, because that's how close are we to optimal, essentially. Okay, so random linear code is really good. And there are upper bounds showing that this is tight. So we can't get better than a log 1 over epsilon factor on the rate for any linear code. So are we done? Well, we're not done because random codes are not efficiently decodable. And what do I mean by decodable? Well, I'll go into this a bit later, but basically an adversary corrupts our code word and we want to undo their corruptions. And if the linear subspace, if the code is kind of random, it can be really hard to figure out how to undo the corruptions and get back to where you started. But for codes that are more structured, they often come with algorithms for decoding. And so we want structured codes that are near the GV bound, so they kind of have some amount of pseudo-randomness, at least from the perspective of having a high rate relative to distance. Okay, and this idea of pseudo-random objects brings us to the definition of something else, which for now, I'm just going to tell you the definition, and it's extremely related to everything we've talked about. So I'll tell you the definition, and then I'll tell you how it's related. This is a pseudo-randomness object. So a multi-set, each of elements of k bits is epsilon biased if a random element from this set looks like a uniform random vector according to a specific class of tests. So what does these tests do? each test specifies a subset of the bits. So like in this diagram, I'm specifying the second bit, the fifth bit, the seventh and eighth bit, and then I take the parity of them. So if like the string we're taking the parity over is truly random, then the parity is equally likely to be 0 and 1. And so what we want of our set big S is that if you take a random element of it, a random vector, and you look at any fixed test, the probability of the parity, like that test, outputting 1 and 0 to be essentially the same. And epsilon measures how close we are to this ideal scenario. So this is like a pseudorandomness object because if we had S like that was like each element of S were truly random, then we would have epsilon be 0. But we want the size of the set S to be small, which is a very important tool in de-randomization. So these epsilon bias sets appear all over, and they can be used to construct other primitives as well. So they're extremely useful. Now, the reason I bring them up in connection to all the coding stuff is they're actually equivalent to epsilon balance codes. So what you do is if you have your set S, just take the matrix where each element of S is one row. And now this is a generator matrix of a code, meaning to generate every element in your code, just do matrix multiplication of this matrix with all possible vectors in F2 to the K. And you'll get a code that is epsilon balanced if you start with an epsilon bias set. And the rate of this code will be K over the number of elements S. So we want we want a relatively small set with a small epsilon as well. Okay, and once again, we kind of get some rate versus distance trade-off. So we have this one object we want to construct with applications both in coding seat theory and in de-randomization. Okay, so what's the state of the art for explicit constructions? Here, explicit just means there's a deterministic algorithm for outputting these codes or these sets. Ta-Shma showed in 2017 that there are explicit epsilon balance codes with rate, this factors from the GV bound, and then this additional factor, which is less than any polynomial in epsilon. It's kind of like inverse quasi-polynomial. So Ta-Shma gave codes that are very close to the GV bound. Okay, and they improved upon the prior state of the arts, of which there were a few depending on which parameters you wanted to optimize, the dependence on epsilon or on K. Okay, and they were all polynomially far from the GV bound, whereas Ta-Shma is within a sub-polynomial factor of the GV bound. Okay, so this is very useful for de-randomization because the codes are explicit. But as they were given in 2017, they weren't yet so useful for coding theory because they didn't come with an efficient decoding algorithm. Meaning this process I described earlier of an adversary corrupts a code word, we want to undo the corruptions. Until more recently, we didn't know how to efficiently decode Ta-Shma codes, but a series of very recent works showed how to decode a variant of Ta-Shma codes. And now they can be used for coding theory as well. Okay, so what is this? Now I want to formalize the decoding problem because, well, then I'll be able to give you Ta-Shma's code combined with the more recent work. Okay, so we have we encoded our code word into W. We encoded our plain text message into a code word W. Then an adversary corrupts it, and then we receive the corrupted message, and we want to undo the corruptions. So the first thing we might want to do is unique decoding, where we ask for, assuming the adversary didn't make too many corruptions, what is the single unique code word close enough to our message. And this is really nice because assuming the adversary didn't make many corruptions, we are done. But this only makes sense if there is a limited number of corruptions the adversary can make. If the adversary makes too many corruptions, more than half the distance, then there might be multiple code words that are both close enough. And so we can't return a unique one. The second task we might want to solve is list decoding, where we return all code words that are close enough to the corrupted message. And this is useful because if this list is small, then maybe we can use some side information to figure out what the true code word was. And the Johnson bound guarantees us that we can get quite a large radius and this list will still be small. Okay, so combining the works of Ta-Shma and Geronimo, Srivastava, and Tulsiani, JST slightly modified the original Ta-Shma codes, so the rate got a little bit worse. This 2/3 became a 5/6. But they show that they are uniquely decodable and list decodable both in almost linear time, within log factors of linear, assuming viewing epsilon as a small constant here, up to a radius which is not quite the Johnson bound, but still very close to 1/2. So still close to optimal. Okay, and this is the state of the art for explicit codes. Now we can also consider non-explicit codes. So Hemingway, Ronzewi, and Wooters constructed codes that are randomized. So what does that mean? So PPT here stands for probabilistic polynomial time, and it's a pre-processing step. So there's a randomized algorithm which is efficient and with very, very high probability, like an exponentially small failure rate, it outputs a code that is good. Like it has all of the criteria on this slide. So it gets rate that is really close to the GV bound. And it's also decodable now, not in almost linear time. Like it's not just a log factor off, but still it's just n power little o of 1. So still very close to linear time. And now also to the Johnson radius. So this is a really cool and useful code. One thing it's not so useful for is explicit epsilon bias sets. It's not explicit. And so you can't really use it for the de-randomization tasks, but still it's a very good code. Okay, and now I'm ready to give our result. We give also probabilistic codes. Their rate is also within this kind of inverse quasi-polynomial factor of optimal. But this is a bit better than what Ta-Shma and JST got. And these are, once again, decodable in almost linear time up to a radius, not quite the Johnson radius, but still quite large. Okay, so just comparing this with the prior works, compared to Ta-Shma's codes, we get slightly better rate in list decoding radius and an arguably simpler construction. Compared to HRZW, we get faster decoding and arguably like a more structured, simpler construction. But more importantly, more than just kind of like comparing, there are some parameter regimes in which our code is the best. But what I think is more exciting is the avenues towards future work. So we give a viable path towards explicit codes with rates within a log factor of the GV bound, like essentially optimal. And the reason for that is the randomness in our construction is isolated. All the randomness comes when we draw a random hypergraph. So if you can give us explicit families of good hypergraphs, our construction becomes explicit. And given even better hypergraphs, which we haven't yet proven exist, but there are some reasons to believe they might exist, we get codes with extremely good rate, essentially at the GV bound. So I'll tell you a bit more about this later, but I think this is the most exciting thing that our ideas hopefully bring us within striking distance of a really cool result, epsilon bias sets essentially at the GV bound. Okay, so now a bird's eye view of our result. So we start with an epsilon 0 balanced base code. Think of epsilon 0 as like 0.1, like it's much larger than epsilon, but still like kind of smallish. And then epsilon, think of it as like 0.001. And we use a base code of Guruswamy and Indik. Then we're going to use something called a parity sampler, which I will define on the next slide. And it gives us a way of reducing the bias of the code, taking a code that is epsilon 0 bias and making one that's epsilon bias. And then we decode using the same JST framework used to decode Ta-Shma codes. Most of our ideas come in the second step. And in fact, the entirety of the remainder of this talk will be the second step. Just I have limited time. And I think it's the most interesting aspect of our work. Okay, so what is this parity sampler idea? Well, I'm first going to just define like what it does, and then talk a little bit about how it's useful and why we might hope it exists. Okay, so we start with some epsilon 0 bias set, or equivalently some epsilon 0 balanced code. And then our parity sampler, so if this is a set of n elements, our parity sampler is just a set of tuples, t tuples, each of an index between 1 and n. And this parity sampler just defines an operation to create a new set. So you have a parity sampler gamma. We can make a new, hopefully epsilon bias set, like hopefully it has small bias, but a new set, gamma of S, where for each tuple in gamma, we create one element of the set. And what do? Well, the tuple gives us t indices. It like specifies t elements of S, and we just add those elements up. Where addition here is just standard element-wise addition. You can think of it as addition over the field F2 to the K, or the vector space. Okay, so now what do we hope to get out of this parity sampler? Well, we want, if we start at an epsilon 0 bias set, we want it to output an epsilon bias set. And we're not making any other assumptions about S, except it started with a pretty good bias. And we want the parity sampler to reduce the bias further to epsilon. Okay, and we just call parity samplers with this property, epsilon 0, epsilon parity samplers. Okay, and suppose we had such a parity sampler. Well, it allows us to amplify the distance of the code, one that is epsilon 0 balanced, so it has distance like 1/2 minus epsilon 0, to one that has distance is epsilon balanced, meaning it has distance 1/2 minus epsilon. And this does come at the cost of some rate. And the rate incurred is the number of elements of S over the number of elements of gamma. So we want gamma to have not too many more elements than S. This means that the new set is not too much larger than the original set. Okay, so this is great if we have it, but should we expect parity samplers to exist? Well, there's a trivial parity sampler. It just specifies all n to the t possible tuples. And it's not hard to show that for any epsilon 0, this is an epsilon 0, epsilon 0 power t parity sampler. And think of epsilon 0 as some small number like 0.1. Taking the power of it vastly reduces it. So this is great. But the downside of this is that it has horrible rate. So it has n to the t elements. So we have this extra factor here of n over n to the t. And it's too costly essentially to get anything close to the GV bound. So we want a more efficient parity sampler. And okay, so I'm just going to say a few brief words about the intuition for why we get to this epsilon 0 power t. And that will give us the intuition for how we might hope to build more efficient parity samplers. This comes from the fact that if you take a random set of indices from gamma, so a random W1 through WT, they are all independent in the trivial parity sampler. So kind of each index is independent. And this allows you to use independence to multiply some things, each of which have quantity epsilon 0, and you get epsilon 0 power t. Now, we don't want full independence because doing so requires gamma to be huge. But instead, we want to kind of de-randomize this. We want a smaller gamma where the indices, they're not fully independent, but maybe they have like some independent characteristics, vaguely. Okay, and this brings us to constructing parity samplers using random walks on expanders. And random walks and expanders have been an extremely useful tool in de-randomization and constructing analogous samplers in other settings. So we start with a graph on n vertices, and we can think of each of them being labeled with a number 1 through n, an index 1 through n. And we want this graph to be a good expander. And then we take gamma to be all length t walks in G. So this walk hits 4 elements. They each specify an index, and that becomes W1 through W4, one element of gamma. This idea was proposed in Ta-Shma's work, building off of unpublished ideas of Rosenman and Vigderson. And Ta-Shma was able to show that kind of at like a very high intuitive level, if you look at how effective this walk is, 1 in every 2 steps works. So choosing optimal expanders, you don't get rate epsilon squared, which is what we hope to get. Instead, you get rate epsilon to the 4th, where the 2 becoming a 4 is due to this 1 in every 2 steps working. Okay, so at this point, we deviate from the path Ta-Shma took. His way to improve this epsilon to the fourth was to take a pretty complicated graph product and show that instead of having one in every 2 steps working, he can take S steps and all but a small number of those S steps will work. And this allows him to get rate quite close to the GV bound. In this work, instead we're going to walk on a hypergraph. I'll tell you how in a moment. But at a high level, we get every single step to work when we do so. Okay, so what is our walk on a hypergraph? So we consider 3 uniform hypergraphs. So each edge is now a triangle. You know, in regular graphs, each edge specifies 2 vertices. Here we specify 3. And each vertex appears in exactly D triangles. Okay, so the walk is specified by a starting vertex and then edge labels telling you where to step. The same way you would specify a walk on a normal graph rather than a hypergraph. But okay, so given this specification, how do we decide what indices gamma outputs? So we start at our starting vertex, and then we take the I first triangle of it. So it has D many triangles, and we take the one specified by I1. And this triangle gives us 2 elements. We use 1 as our next V, kind of where we'll start from in the next step, and 1 to output. So 1 is output by our code, W1, or output by a parity sampler. And then we do this again. You know, we take the I2 triangle, get a new starting vertex, get a new bit to output, and we continue. So we take a walk and we kind of output bits from the spine of this walk. They're like not quite where we walked. We output W1, W2, W3, W4 in this setting. And this didn't come out of thin air. So for just a little bit of quick intuition, Ta-Shma was able to show 1 in every 2 steps work. So we want to like take 2 steps at the same time, like do 2 steps for the price of 1. So we viewed that as moving from V0 to W1 to V1, V1 to W2 to V2. And that eventually, with some evolution of ideas, became the random walk you now see now on a hypergraph. Okay, so how good is this random walk? Well, it depends on the hypergraph you start with. So we need a notion of expansion on these hypergraphs. And there are many different notions for expansion. So we're going to consider this one, which I think is new, but it's a very reasonable notion of expansion. It is a generalization of spectral expansion of graphs. So if you get rid of all the W's here, you recover just the graph being a spectral expander, where the graph is just like edges between X and Z. Sorry, to get rid of the Y, then you get that. Okay, so this is some generalization. It has lots of terms, and I won't go to them all in detail, but it's a very reasonable generalization. And one way for us to say it's reasonable is that we can show that a random D-regular hypergraph satisfies our definition with a good parameter. So we get lambda to be within a log factor of 1 over root D. And we know that the best you can possibly do is you can't do better than 2 over root D. So we're within a log factor of optimum. Okay, so how do we use this? Well, we show that the walk I gave you on 2 slides ago, which specifies a parity sampler, it outputs a parity sampler with how good it is depending on lambda. It outputs an epsilon 0, epsilon 0 plus lambda to the t parity sampler. So, the best we should hope for is epsilon 0 power t. So this lambda is like a deviation from optimal for this parity sampler. Now, if you take the lambda guaranteed from a random hypergraph by our lemma and optimize parameters, you get this very close to epsilon squared within like an inverse quasi-polynomial factor. Now, if you got lambda that's 2 root d, which kind of is analogous to Ramanujan graphs, hopefully these like Ramanujan hypergraphs exist, but we don't know if they do, then using just like a slightly more complicated walk, we're able to get within a log factor of optimal. Okay, so where does that leave us? Well, we have these big open problems on constructing these hypergraphs. All we know right now is that random hypergraphs are pretty good. But we don't know, maybe random hypergraphs are essentially Ramanujan. And if you could show a random hypergraph is this good, then we get our construction gets you almost at the GV bound within a log factor. Even non-explicitly, this would still be super interesting. And then the second question is, can we make it explicit? Can we find explicit hypergraphs that either are within this log factor of optimal lambda or really are at Ramanujan perhaps? And then our construction becomes explicit. So yeah, I hope someone in the audience finds this interesting and comes up with a very cool construction of these hypergraphs. Yeah, thank you for your time. Goodbye.